Hello. We are going to continue with 2.2 more on functions and their graphs. Okay, let's go ahead and look at increasing, decreasing, and constant functions. So if a function is increasing on an open interval I, or a function is increasing on an open interval I if f of x1 is less than f of x2, whenever x1 is less than x2 for any x1 and x2 in the interval. So what does that mean? If we look at this graph right here, there's our f of x1, which is less than f of x2. So y1 is less than y2. And then we've got x1 is less than x2. And you can see that increasing, so it rises from left to right. Okay, next one. A function is decreasing on an open interval I if f of x1 is greater than f of x2 whenever x1 is less than x2. So notice that the x1 and x2, I mean, these are both like x1 is less than x2. It's the y value, the f of x, that changes. So a decreasing is right here. We see that f of x1 is greater than f of x2. x1 is greater than or less than x2 still. Those haven't changed the spots. It's the y values that change. y1 is greater than y2. And it means that since it's decreasing, it falls from left to right. Then we have the third one, which is a constant. So a function is constant on an open interval I if f of x1 equals f of x2 for any x1 and x2 in the interval. So we can see that it's just a horizontal line. X1 and x2 can be anything. It doesn't matter. F of x1 and f of x2 just stay the same. So the y value is the same. Okay, so let's look at an example. State the intervals on which the given function is increasing, decreasing, or constant. So if we look at, oops, oh, it zoomed. Come on, there we go. Increasing first. So where is it rising from left to right? So if we start coming from the, down here up, we can see that it increases up until here. So negative infinity to negative 1. After that, it is decreasing because it's going downhill from negative 1 to 1 right here. And from 1, it's going to increase again. So 1 to infinity. There is no interval for the constant, so there's none. Now, notice that when I wrote the intervals, I wrote them with parentheses. Anytime we have a negative infinity and infinity, we're going to write, it's going to be a parentheses because it's not a set point. It keeps going and going. For the negative 1 and 1, those are both open as well because it switches. At negative 1, the increasing switches to decreasing. So there's really not, neither one can be exactly like negative 1 and 1. So that's why we use the parentheses and not the brackets. Okay, so these are the intervals on which a function increases and decreases. We're using the x values for that. Next, we're going to look at there are definitions of relative maximum and relative minimum. So a function value f of a is a relative maximum of f if there exists an open interval containing a such that f of a is greater than f of x for all x does not equal a in the open interval. So if we look at, here's your relative maximum right here, a and f of a. So that is, okay, so next one, a function value f of b is a relative minimum of f if there exists an open interval containing b such that f of b is less than f of x. Again, relative minimum is right here, b and f of b. So it's where it's like down on the bottom. The word local is sometimes used instead of relative. So you might see local maximum and local minimum also instead of the relative. All right. Next, we're going to use this graph to find the relative maxima and minima for it. So, this function has a relative maximum. I'm just making sure that I'm using the same colors. So function has a relative maximum at x equals. So we're going to find the x. Our relative maxima is right here. So x equals -1. And then f has a relative minimum at x equals, that is right here, and that would be 1. All right, next what we're going to do is we're going to test for symmetry. So the graph of the equation is symmetric with respect to the y-axis if for every point xy on the graph, the point -xy is also on the graph. So what we're doing when we're testing it, we're substituting -x for x in the equation, and it should result in an equivalent equation. Okay, the next one is the graph of the equation is symmetric with respect to the x-axis if for every point xy on the graph, the point x -y is also on the graph. So we're substituting -y for y in the equation, and it results in an equivalent equation. The graph of the equation is symmetric with respect to the origin. Origin is the point 0, 0. If for every point xy on the graph, the point -x, -y is also on the graph. So what we do is we substitute -x for x and -y for y in the equation, and it results in an equivalent equation. Okay, so that's what we're going to do next is test for the symmetry. We're going to start with the y-axis here. So we have y equals x squared minus 1. And like I said, we're starting with y-axis. So for the y-axis, we are substituting -x for x. So our original one is y equals x squared. Actually, you know what? Let me write it like this. Y equals x squared minus 1. And we're going to substitute x for -x. So y equals negative, oops, negative x, and that's inside the parentheses because that's the base, squared minus 1. Oops, I keep touching this somehow, so it keeps moving. Minus 1. So negative x squared is going to be x squared minus 1. So this and this equation is the same. So the graph is symmetric to the y-axis. Okay, next we're gonna look at x-axis. And again, we're starting with the exact same function. And for the x-axis, we are substituting negative y for y. So what we're going to do is we're going to write negative y equals x squared minus 1. Now, what we need to do is we need to get rid of this negative. So this is the same thing as a negative 1 times y. So we're going to divide everything by negative 1. So we get y equals, and we're dividing x squared by negative 1. So that gives us negative x squared, negative 1 by negative 1. And that gives us plus 1. So now if we compare these two, they are not same. So the graph is not symmetric to the x-axis. All right, next one is going to be the origin. So if we go back here, we see that we are substituting negative x for x and negative y for y. So negative x for x and negative y for y. So we're doing both substitutions. So it's negative y equals negative x inside the parentheses squared minus 1. Again, we need to, well, first, we're going to do the this part right here. So negative x squared is going to be x squared minus 1. Again, we have that negative sign in front of the y, so we're going to go ahead and divide by negative 1. So we get y equals negative x squared, because x squared, so this is the same thing as x squared divided by negative 1 minus 1 divided by negative 1. Negative x squared plus 1. So again, if we look at these, they are not same. So the graph is not symmetric to the origin. So what does this graph actually look like? If we sketch it, here's our x and there's our y-axis. It looks something like this. So if we look at it, yes, it is. We can see the symmetry for y-axis, but x-axis and origin, there's no way. What it means is that if, for example, if it was drawn correctly, if we take the y-axis drawn on a paper, take the y-axis and fold it along the paper along the y-axis, both of these sides should go on top of each other, which, if it is, I mean, I'm just sketching it, but if you're drawing it actually accurately, so it should be easily seen that that's the case. Origin and x-axis, nope, those are not. All right, next thing we're going to define are even and odd functions. So we're going to start with an even function. So the function f is an even function if f of negative x equals f of x for all x in the domain of f. And the graph of an even function is symmetric with respect to the y-axis because we're substituting negative x with x, and it's the same one. Okay, next, the function f is an odd function if f of negative x equals negative f of x for all x in the domain of f. So the graph of an odd function is symmetric with respect to the origin. Okay, so now we're going to go ahead and identify even or odd functions from equations. So we're going to start with an even function. And now remember that f of negative x equals f of x. So the right side of the equation of an even function does not change if x is replaced with negative x. For the odd function, so basically we're doing, this is backwards from when we did the definitions. So for an odd function, f of negative x does not equal f of x. Hold on, no, that's not correct. I was like, that's not correct. F of negative x equals negative f of x. So every term on the right side of the equation of an odd function changes sign if x is replaced with negative x. Okay, then we have the third case where neither even or odd. So that means now that f of negative x does not equal f of x, and f of negative x does not equal negative f of x. So the right side of the equation changes if x is replaced with negative x, but not every term on the right side changes sign. Okay, so let's go ahead and look at the example here, identifying even or odd functions. So is this function even, odd, or neither? So we're going to go ahead and replace x with negative x and see what happens. So h of negative x is going to be negative x to the power of 5 plus 1. Well, we can see that this becomes, because the exponent is odd, we're going to have a negative x to the power of 5 plus 1. So this here means that h of negative x is not h of x. So it is not even, because it would need to be in this form if it was. For odd functions, it should bring the negative outside here, but it does not that because the plus stays the same. That doesn't change from here. It's only the negative that changes. If the sign in front of the 1 changed, then it actually would be. So this is not odd. So that means that this is neither. All right, next we're going to look at piecewise functions. So that is a function that is defined by two or more equations over a specified domain. And that is called a piecewise. Oops. piecewise function. So we're going to go ahead and evaluate a piecewise function here. So you can see that here's our function. And c of g, so it is 40 if g is between 0 and 15. And then it's this equation if that should be a g and not a t. G is greater than 15. So we're going to go ahead and find c of 5. Well, 5 goes in here, in this one right here. So that means that our answer is just going to be 40. So we need to find where this number falls. Now, if we go and look at c of 50, well, that's greater than 15. So we're going to have to use this equation to solve it. So 40 plus 0.60 parentheses 50 minus 15. And when we plug all that in into a calculator, we get c of 50 equals 61. So you have to make sure that you're looking at the equation that is, the domain is correct for that equation. Okay, now we're going to go ahead and graph a piecewise function. So we've got f of x equals 3 if x is less than or equal to negative 1, and we've got x minus 2 if x is greater than negative 1. Let's draw a coordinate plane first, and I'm going to do 1, 2, and 3. 1, 2, and 3. Negative 1, negative 2, and negative 3. Negative 1, negative 2, and negative 3. Okay, so we're going to go ahead and look at this part right here first. So x is less than or equal to negative 1. So what we need to remember when we're looking at the domain is that we're, doing equal to or less than negative 1. So we're going to start with negative 1 and go down, negative 2, negative 3. Well, we see that f of x equals 3, so it doesn't matter what the x is, your y is going to be 3. So this is going to look like negative 1 and 3 is right here, negative 2 and 3 is right here, and negative 3 and 3 is right here. So we're starting here and going that way. Okay, let's look at the other part of the piecewise function. So x is greater than negative 1. We're still going to go ahead and calculate the negative 1 so we know where it starts, but we're going to go to greater, 0, 1, 2. And yes, negative 1 is not included, so we have to remember to use the circle with that one. And then f of x, we're using the equation for it, so that is x minus 2. So negative 1 minus 2 is going to be negative 3. So our first point is negative 1 and negative 3. And that is going to be a circle because it is not included. Notice there's no equal sign. It's just a greater than. Okay, let's calculate the next point. 0 minus 2 is going to be negative 2. So 0 and negative 2 is right here. Next one is going to be negative 1. So 1 and negative 1. And next one is 2 minus 2, which is 0. And it's going for the greater. And now this is not going to be a straight line because it's my, it should be a straight line. My coordinate plane is not straight. So, all right. So that was the piecewise function. We've got one more thing in this lesson, which is the definition of the difference quotient of a function. So we have the expression f of x plus h minus f of x divided by h. For h cannot equal 0 because we can't divide by 0. This is called the difference quotient of the function f. So, we're going to go ahead and do that for this function right here. So our f of x is negative 2x squared plus x plus 5. Now, what I want to do is I'm going to calculate the f of x plus h that we're going to need here. So I'm going to plug in the x plus h where the x is. So negative 2x plus h inside parentheses squared plus x plus h plus 5. Now, before I use the difference quotient, I'm going to simplify this so that I have everything done. Foiling or using the a plus b squared formula. Either way, we're going to get negative 2 stays, and I'm going to put parentheses so that I haven't distributed the negative 2 yet. But what we get from here is x squared plus 2 times hx plus h squared. Again, this is the same thing as x plus h times x plus h, and you can FOIL it to get what I got. Now, we can drop the parentheses here because there's nothing, they're not needed. Next, I'm going to distribute the negative 2 in front of the parentheses. So negative 2x squared minus 4hx plus, I'm missing the 2, negative 2. Come on. Negative 2h squared plus x plus h plus 5. Okay, I don't think I'm able to combine any, there's no like terms. So this is my f of x plus h. So now what I'm going to do is I'm going to go ahead and use this right here. So I already calculated the f of x plus h. So this is our difference quotient right here. So I'm going to plug it in. Again, the difference quotient is f of x plus h minus f of x divided by h. So plugging this in first, negative 2x squared minus 4hx minus 2h squared plus x plus h plus 5. And now subtracting, and now we need to make sure that this is a minus sign. So there's going to be a minus sign. And now I'm plugging this in inside parentheses. So because I have to distribute the minus sign to everything. And then it's going to be divided by the h. Okay, next, I need to go ahead and I'm going to switch colors here. This first part does not change yet. We're just keeping it as it is. What we need to do first is distribute this negative here. So negative and a negative becomes a positive. Negative and a positive is a negative, and negative and a positive is a negative. Everything divided by h. Okay, now we can start looking at, is there something we can actually cancel out? Negative 2x squared and positive 2x squared, those cancel out. Then we have a positive x and a negative x that cancels out. And we have a 5 and a negative 5. So all those cancel out, and we end up with negative 4hx minus 2h squared plus h divided by h. Now what we want to do is every single one of these has h in it, so we're going to factor h out. So we end up with negative 4x minus 2h plus 1. Remember that this is 1 times h, so when we take the h out, there's still a 1 left. And then we have h down here. Well, the h divided by h is going to be 1, so those cancel out. Again, we need to make sure that h does not equal 0. And our difference quotient is going to be negative 4x minus 2h plus 1. All right, that's it for this lesson. Let me know if you have any questions. Bye.